All right, in this video, we're going to take a look at how we can actually use or conduct a hypothesis test using a confidence interval. What we're going to see is that the questions that we're about to ask are going to be questions that we've kind of already asked before. At least this first example here, and example number 5 is. We saw this example about bystanders performing CPR correctly back in 7.1. And we're going to try to do the exact same question to reach the exact same conclusion, just taking a slightly different approach. Okay. So what we're going to see here is that for the most part, nothing about the process of hypothesis testing is going to change. Let's just kind of jump right into it and see what we got. All right, first I'll reread the problem. Bystanders perform CPR correctly less than half the time, according to a USA Today article, which noted that among the cases in which bystanders gave CPR, 305 performed the CPR correctly and 357 did not. Test the article's claim at a 3% level of significance. Okay, so we know that here we're dealing with a mystery percentage. And we can see that the article is claiming something about the percentage of people that do CPR correctly. Seems like they're claiming that it's under half, which means that my other hypothesis would have to be equal to half. Again, remember, those always have to have the same numbers in them. Okay, these are the same hypotheses, again, we worked on back in 7.1. And you could even pull out the notes from that section to confirm that we're not really going to have anything different here. Okay, what's going to be a little different now is I don't have this kind of step of a test statistic. I'm not going to go ahead and try to compute like a z-score and do that sort of stuff. But I will try to list out the sample evidence and check conditions to create a confidence interval for that mystery value of p. Okay, so most of this stuff is still similar to what we had done before. So my evidence. I know that we asked here a total of, let's see, 305 plus 357 people, which is 662 total people. Out of those 662, only 305 did the CPR correctly. So the p hat that we come up with is 305 out of 662. And I think on the calculator, we came up with that value as 46.07%, or 0.4607. I'm going to have to go ahead, and if I want to do a confidence interval, I'm going to have to run the checks for that confidence interval. That's no surprise. Notice that that's super easy. Right here underneath confidence intervals, I already have my checks written down. So I'll just go right there to conduct them. Okay, so let's see. First check. I need 20 times my 662, and that's going to turn into 13,240. And the question is that less than or equal to n? If capital N is all the people that have ever performed CPR, this seems pretty reasonable. There's probably been more than 13,240 people that have performed CPR. 2. I need to take 662, and I need to multiply right now by the value of p hat, because I'm going to try to create this confidence interval. So I'm going to do this, 1 minus this value, and I'll just tell you here for the sake of time that I ended up with 164.4775. You can crunch that number yourself to double check me. Okay, so I know that p hat then has a normal distribution, and that means I can go ahead and actually construct the confidence interval. Here's the hard part. What confidence level do I want to use for this interval? Note that the problem doesn't really tell me this. This is what's kind of difficult. Let's go down here to the analyzing step. Here's what we know. Alpha was given as 3%. Remember that our value of alpha, that level of significance, is kind of, again, our measure of rarity. It's if something falls into that bottom 3% or the top 3%, then we know that something's bad or rare. So I'm going to go ahead and draw a picture here, kind of like what we drew in the past couple of videos, or the very first video for this section, where we had values of p hat kind of on a number line. Now, what I know right now is that on the low side, since this is a left-tailed test, we would feel unconfident in p being 50% if we saw that we had too small of a value of p. So there's a bottom 3% down here that's bad. When we construct a confidence interval, remember that we went up and down from the average by the same amount, and we constructed some value there. But if our distribution is symmetrical, then it should be the case that there's kind of an implied bad 3% on the top end. So if there's a bad 3% that's also on the top end that's not being included, we should be able to tell what percentage our interval is supposed to cover. And here it looks like that would have to be 94%, because I have 6% in red, so the remaining 94 is good. So I need to construct a 94% confidence interval. Okay, this is kind of a strange construction, but it relates back to what we did again at the very beginning of this video. If you don't recall that from the beginning of the video, or beginning of this lesson, then I would ask you to go back to that first video and rewatch that kind of construction. You can see where we make these pictures. We'll do this again in the next example as well. Okay, so now I'll go to the calculator and I'm going to try to construct this interval. So let's see. I can go down and construct a 1 prop z interval. Let's see where we're at. Oh, there it is, option A, 1 prop z interval. We had 305 out of 662. We built a 94% confidence interval. Here's the interval I end up with. It's 0.4243 to 0.4972. Okay. Now notice, this interval is what is going to help us understand kind of how good our hypothesis fits. Right now, we're again testing hypothesis 0, H0, like we always do. So right now, we're walking into this problem saying, you know, let's just say for the sake of argument that P is 0.5. Would it be weird to get the sample percentage that we saw? When we look at the interval, we kind of go, well, wait a minute. If you're telling me that P is supposed to be 50%, and we're 94% confident that the real value of P is in here, does 50% seem like a good fit anymore? I mean, I'm really confident that the real value of P is apparently not 50%. It looks like I'm starting to become more confident that it's probably lower. So notice down here, I kind of always have these two possible outcomes. The believed value of P, which comes from H0, is in the interval, or the believed value of P that comes from H0 is not in the interval. And right now, we're kind of seeing this because 0.5 is not inside of this interval. So here's how I would write my two-sentence conclusion. I would say, since the interval does not contain the believed value of P, which equals 0.5, we reject H naught. That doesn't seem like it's a good fit anymore. So then I should be able to state what I believe. Therefore, we believe that the percentage of bystanders who perform CPR correctly is under 50%, right? We're agreeing with H1. Hopefully this doesn't feel like it's too different than the ideas that we did back in 7.1. It's the same kind of conclusion, it's the same kind of construction, except that now we're just using an interval. And instead of doing computations with p-values and other sorts of things, we just build the interval and make our determinations from there. Okay, I'm going to take a look here at one more problem in this video to kind of wrap up this section. Let's take a look at this one together. Example number 6, this is a new one. In 2001, a national vital statistics report indicated that 3% of all births produced twins. Is the rate of twin births different among very young mothers? Like maybe if, you know, a woman was to get pregnant very young, does she have an increased chance of having twins? Let's see, data from a large city hospital found that 11 sets of twins were born to 469 girls. Test the appropriate hypothesis using a 5% level of significance. Okay, so I know I'm going to set up my hypotheses, and I can see that I'm looking for a mystery percentage. I want to know the percentage of twins, or the percentage of births that result in twins for these teenage girls, right? For all teenage girls, for very young mothers. So it seems like right now, the question is the rate of twin births different than 3%? Well, how could I communicate in a hypothesis that the percentage is different than 3%? Well, yeah, if it's different, I might be able to word it or state it like this, like it's not the same as 3%. It's something else. It's different from that. And that would mean that in the other hypothesis, I have exactly 3%. Remember that nothing about the actual data values, like 11 out of the 469, none of that matters at all in terms of writing your hypotheses. It's all about the question that's being asked. Okay, now I can know my sample evidence and then do my checks to make an interval. Evidence. Let's see. We had 469 teenage girls. There was a result of 11 births that were twins. And so if I compute a percentage for that, that's 11 out of 469. If I crunch that out on the calculator, I think I end up with 0.0235. So it is a percentage that's under 3%, but that might just be, happening by chance. So let's do the checks to see if we can determine what things are likely or unlikely. So let's see, my first check is going to be 20 times 469. When I crunch that out, I get 9380. And I could ask, if there were 469 teenage girls that teenage mothers, then are there more than 9,380 individuals that have been teenage mothers? And, well, that seems very, very safe to assume. If I have then my second check, I can see here again, I'm going to be using my value of p hat. In this calculation. If I was to crunch this all the way out, I get a number like 10.7625. And of course, that is indeed bigger than 10. So I know it's safe to build a confidence interval. Again, the only thing that the problem doesn't tell me is the confidence level. But again, I'm going to go ahead and I'm going to draw a picture. Now, something here will be slightly different in this picture because notice we again have a two-tailed test. Remember that when we computed a p-value in a two-tailed test, we often had to shade both tails. Well, in the same way, when we deal with this value of alpha, this bad region at 5%, in a two-tailed test, that 5% is always going to be divvied up between each tail, which means in this case, I would have 2.5% on each individual side for a grand total of 5% bad stuff. This always happens in a two-tailed test. That then means that my confidence interval should cover what percentage of the distribution? Well, that would cover 95%. So I'm going to construct a 95% confidence interval. To build this interval, I will go to the calculator and run through all my data. Let's see. Here we had 11 out of 469, 95% confidence interval. I'm going to write down what this interval looks like. And so we can say that we're 95% confident that the real percentage of teenage mothers that give birth to twins is somewhere between 0.0098 and 0.372. Now keep in mind that we started this under the assumption again that H0 is true. That's the one that's the hypothesis we always try on to see how it fits. And that hypothesis said that P is 3%. So we're pretty sure now though that P is somewhere between here. How does 3% actually feel? is 3% in that interval? Well, if you look at the numbers, I guess we would have to say yes. 3% is definitely smaller than what I have on the right edge. So 3% is in the interval, which means that it seems like 3% isn't a totally crazy guess. So I'm going to go ahead and state the following. I'll say, since the interval contains the believed value of p equaling 0.03, we do not reject H naught. We're going to stick with it, right? It seems pretty reasonable. So we would say we have no reason to doubt that the percentage of teenage mothers who give birth to twins is 3%, right? We don't have any reason to doubt that. We didn't have enough evidence to say that it was something different. This process of using confidence intervals is something that, again, takes a little bit of time and effort. You can actually go back through and do every single regular hypothesis test almost a second time just with the confidence interval approach and guarantee that you always get the same answer. When it comes to doing these sorts of problems in homeworks or exams, if I don't explicitly ask you to use a confidence interval, that means I will always be asking you to use instead this regular hypothesis test approach. But if a problem says use a confidence interval to test, then you must use the confidence interval approach. Okay? If you got questions on this, again, please make sure you practice with the worksheets and stop by our online office hours to ask some questions. All right, I will see you in the next section for 8.2.